Sir,
Sir.
sorry, sir. Let me
Yes.
start or we have to wait for 2 minutes.
You can start,
Okay,
sir.
sir.
Okay. Shukma, sir.
Sir.
Yes. Are you ready, sir?
Yeah, I'm ready, sir.
Yes, sir. Uh, Good evening, our valuable participants. On behalf of NPR College of Engineering, Technology, Matham Chemical, Department of Mechanical Engineering, we welcome to the second day Atal AICTE Atal sponsored faculty development programs. Uh, Here, uh, our esteemed resource person, Dr. G. Shokmar, sir, with us.
Sir.
He is former, is it audible, sir?
Yes, sir. Audible, sir. Audible.
Yes, yes, yes. Dr. G. Shokmar, sir, is a former professor, a present industrialist. He has completed his PhD in the area of joining dissimilar material using CO2 laser system. When I talk about this, uh, his company name is Adi Burhan Powder Coating. The company is established 2018. Is leading service provider in the powder coating industry located in Coimbatore, Tamil Nadu, India. We specialized in developing and applying high performance powder coating for superior durability, corrosion resistance, and aesthetics of materials. Uh, the company is creating a customized powder formulation and tailored specific client needs for the various materials with the high additives and finishing qualities. The company aims to uh, providing a satisfaction of customer services with increasing production capacity and exploring new market needs and industries needs as per the requirements of the present scenarios. Adi Bhagavan Powder Coating has revealed industry award from the Conferred of Indian Industry, that is CII New Delhi, appreciations awards from educational institutes for their services, excellent services. Uh, Dr. G.K. sir with us. Uh, Sir, welcome to this second day FDP first session. The forum is yours. Please welcome, sir.
Okay, sir. Thank you, sir. Thank you so much. Shall I start, sir?
Yes, sir.
Okay, sir. So I'm very happy to be a part of this knowledge sharing session, Atal Training FDP program of days 2, session 3. Hello.
Yes, sir. Is it audible? You can proceed, sir.
Yes, sir. Yes, sir. If it is any issue, you know. Uh, about mastering part of discolor models of CO2 laser systems. Uh,
Sir, Ziki, sir. Soma sir.
Sorry, he's left here.
Sir, I think. Sir, please check it is network, sir.
He's left from the meeting, sir. You can please call him.
It's joined, I think, sir.
Hello.
Yes, sir.
Sir, now it is okay, sir?
Yes, sir. Yes, sir. Okay. You can share the slide, sir. Slide is not
Okay.
it. Yes.
Okay, sir. Okay, is it visible, sir?
We'll wait, sir. Sir, if you have any trouble to share the slides, I can operate from here, sir.
I will share again, sir.
Okay.
Is that okay, sir?
Slide
Okay,
is not
okay.
now only is visible, sir. You
Okay,
can
sir. Okay, sorry for the interruption, sir. Okay. So, so need for dissimilar materials. So what is the need of dissimilar joints? So that's we discuss first. So the techniques for joining dissimilar metals are becoming increasingly important in the manufacturing of hybrid structures and components for engineering applications. So before that, we are doing a part or structure with instead of that, uh, conventional welding joining methods, we can't able to achieve the proper strength if it is whether necessary of the hybrid materials. That is to join aluminum with steel or aluminum with copper or steel with nickel. The conventional methods aren't able to give the proper strength which we need. So we didn't touch that part. So nowadays, uh, um, since we are having the more advanced technology, it's highly possible to mix up the or join the dissimilar materials for a low cost and low cost with same strength achievement. So welding of joining ferrous and non-ferrous metals has benefits like better mechanical properties, metallurgical properties, high corrosion resistance, fatigue failure resistant, and also importantly in industrial aspects, high economical benefits. So these are all the things we are discuss. Huh? So, dissimilar welding is more challenging task, actually, both technically and scientifically. But it has the vast application in petrochemical, then naval field, nuclear power generation, automotive, and electric industry. So, dissimilar metal joining, normally we say DMJ, is generally used to fulfill the design criterion, strength requirement. That is, before that, even though we are not able to achieve our or our requirement, the challenging of doing dissimilar joints, we go with the formal base metals. So we can achieve our goals as per the design requirement now. The cost cutting also. The DMJ is needed to save the novel and expensive materials. That means no rare materials. We can avoid the rare materials by using the dissimilar joints. Uh, so by the way, we can save that novel materials. Also, the cost cutting process. It's a mixed. No, it's a example of an automotive industry. An example of an automotive industry that some example no so the which has more hybrid materials, dissimilar materials in a car body. Aluminum is 53 percentage and steel 36 percentage, FRCs 4 percentage, others 7 percentage. So I'm giving some dissimilar joint products, the need of dissimilar joints I'm just. Then, for example, Honda NSX manufactured with aluminum was 140 kilogram lighter than that manufactured with the equivalent strength with rigidity of steel. No? So they replaced aluminum for steel, and by the way, they reduced to 140 kilograms of weight. So by reducing the weight, we can achieve our more economical as well as mileages. Then here another one part separation. So this car body have aluminum, no 6000 series. Then door inner 5052 and body skeleton 5182. So the utilization of aluminum alloys as a replacement of steel in a body in weight assembly promises the most weight reduction of 27%. So these are all our design goals. But the thing is we can't be able to achieve the proper dissimilar joints using conventional methods. So how to achieve our strength for the particular part is the challenge. So it's a common applications of laser beam welding. So we discussed about conventional method. Then we are now discussing about laser beam welding and its application. Welding of car bodies, transmission components, heat exchangers and pipes, automobiles, aerospace industry, and marine. So it's one example for dissimilar joints. Nuclear power plant pressurized water reactor, PWR system. Here, so the system needs the exact, economical, and efficient process. So in order to achieve the efficient process, the dissimilar joints are necessary. So here, in heat exchangers, tube and tube sheet. Okay, tube and tube sheets are there. Here before heat exchangers are made of a single material. But in order to change the tube sheet and tubes, we can achieve more efficient heat exchangers. So this is the concept. This is a simple example. Actually, the area is so vast. We can In fact, we can play with the systems. Okay, we can do anything. If you are resourceable, we can do anything technically to achieve the dissimilar joints. So the requirement and the scope is vast in this area. So it's another example of multi-material joining in aircraft engine. So titanium alloy. So it's an aircraft engine with a mix-up of different materials. So if you are capable of giving a better strength with a dissimilar joint with advanced systems, that is currently necessary. So it's a typical examples of laser welded joints. So it's a butt joint, lap joint, T-joint, flange, and linear, circular. So everything. So whatever the things we are doing by using conventional methods can able to do in the laser systems. So it's a small survey of about dissimilar joints. So a survey saying that it's a common research and development in the academic and industry aspect. They are focusing on aluminum. So they are again titanium, copper, and other polymers, magnesium, and ferrous is getting its spaces. In that aluminum with magnesium, aluminum with the copper, aluminum with the ferrous, and aluminum with the aluminum composites, aluminum with the titanium. So these are all the research scope and the research process are done already. So why laser beam welding? So in fact, the thing is, we can able to achieve the dissimilar joint by using the conventional methods. That is the fact. We can able to achieve. The goal is by using the laser systems, we can give better strength without changing the. So that is the thing. So laser beam welding has high potential in joining dissimilar materials, especially exclusively laser beam welding. So laser beam welding is suitable for conductive materials due to concentrated energy for melting. The laser beam is a non-contact flexible tool. The power intensity distribution can be changed for the enhanced productivity. So dependency of the productivity, we can achieve the goal also. Then the main thing is the low heat input provides a narrow heat affected zone. So this is and comparing with the conventional methods. So heat affected zone. No? While we are going for a welding joint, so there is a huge amount of heat produced. So unnecessarily the base metals getting changed their physical and chemical properties. So that the thing we can't able to achieve the proper mechanical and metallurgical properties in the joints. So that is the thing. So in due to low heat input and the low heat affected zone gives the better strength in comparing with the conventional joining methods. So other than that, it's possible, highly possible to join the different materials by using the methods. But the thing is, you can achieve the same without changing the base properties. So laser beam welding is a fusion welding process in which two metal processes are joined together by use of laser. The laser beam provides concentrated heat source focused to the gap between the two metal pieces to be joined. So here another one advantage by using the laser beam welding is we don't want any preparation for the joint. Even a single small gap is there, so we can't able to create a V groove or preparation for the welding and all. Even filler materials also not necessary. If it is necessary, it is dependent on the base metal. We can use filler metal. Even without filler metal, without any preparation of the base metal, we can achieve dissimilar joints. So this process can be used for high volume application in the automotive industry. So normally that heat affected zone is very narrow. you can see in the picture. So that narrow affected zone normally we call keyhole penetration. Keyhole is like a deep penetration, not the width penetration. So laser welding is a high power density fusion welding process that produces the high aspect ratio. No, aspect ratio is not depth with this width. So what we need in the joint is less width, more depth. So the penetration will be more and intense. So high aspect ratio is there. So relatively low heat input when comparing with the arc welding process. So another one better example with the laser is we can join multiple pieces of materials. We can't be able to do the same with the conventional method. If we are taking 1 mm, 1 mm of 4 different strips, we can do it in a single stroke without changing the property, and we can achieve the same. So conventional methods won't work out with that. Spot welding we do. Spot welding we can do 2 or 3 strips we can do. It depends on the power of the machine and the thickness of the strip. So laser welding is not about that. So if with the limit of the power, we can do more strips. The penetration will be very depth. The laser beam produces keyhole mode heat transfer, enables very narrow heat affected zone. Due to its high processing speed, the dimensional instability is significantly reduced. That's what we need. Laser welding can be performed on materials of very thin sheets, also thick plate welding. Uh, it's another better advantage. So in conventional methods, in a single machine, doing welding on thin sheets as well as the thick plate is a challenge. So the process is frequently used in high volume applications. No issues. Okay, so the types of laser beam welding. There are 2 types commonly. More types are there. So we are classifying that multiple types into 2: solid state lasers and gas lasers. Solid state lasers type of laser uses one of solid medium ruby, chromium in aluminum oxide, then neodymium in glass, ND glass lasers normally we call, and neodymium in yttrium aluminum garnet, NdAg lasers. So we call ND lasers, NdAg lasers. So it's about CO2, gas laser. So here, the high voltage flows through the tube and reacts with gas particles, CO2, gas particles, increasing their energy in turn producing light. So high voltage allows and flows through the gas particles, that resonator. The gas particles are triggered. By the way, we are getting increased energy. So that converted into, then we are focusing that energy by using the mirror. So we are utilizing it. And focusing lens is a major part. So the positioning of focusing lens on the gap is a setting. That setting will take some time. So once we set that, we can go for mass production. So it's a lens, focusing lens. So another one is shielding gas also we are using. So welding direction, shielding gas nozzle. So that yellow color is a keyhole welding. So CO2 laser welding. Then why we are going with CO2 laser welding? In the sense, 90% of the process we can do without fillers, filler material we can achieve. Moreover, CO2 lasers are so powerful. We can achieve, 5 kilowatt to 10 kilowatt laser will be comfortably doing 7 mm to 15 mm of thickness in same speed. So 15 mm plate, 7 mm, no, 7 mm to 15 mm, up to 15 mm, we can do with 5 kilowatt to 10 kilowatt lasers. Going with less power, uh, definitely initial cost is so high. It's about crores. So if it is in need of uh, more thickness in plate for our application, then we go for CO2 lasers. Then we are just doing with only less than 5 mm or 7 mm plates. In the sense, we use the Nd:YAG lasers. So this can eliminate the need of V joint preparation. So low heat input in material each side of weld joint, very low thermal distortion of the workpiece occurs. Welds can be made very close to heat sensitive components. So metallurgical damage such as severe grain growth and extended hardness are reduced. So these are all the major problem with the material. No, mm, we are in order to find the strength of a joint or strength of a material, we normally go with a tensile and a hardness. So CO2 lasers won't change the property of the base metals. So high production and process flexibility. Then multiple layers of material can be lapped and welded in a single pass. So a wide range of different joint configurations and dissimilar metals thickness can be handled. So the ability to manufacture a product using a number of different metals alloys greatly increases flexibility in design and production. If you are your hands are totally freed to design without considering the manufacturing manufacturing struggles, so we can go with the better designs. We can able to achieve the 90 percentage of the product as per the design. So this is the thing. Then a property such as heat, wear, and corrosion resistance can be optimized. We can get better products. So joining of dissimilar metal combinations, however, challenging task. Even though, so by using CO2 lasers, large differences in the chemical can be used. So so laser welding, a high power density but low energy input process provides solution to a number of problems commonly encountered in the with the conventional joining techniques. So this is the reason why we are shifted ourselves to lasers and CO2 laser. So industrial lasers are used for welding, cutting, drilling. So it's a normal applications of laser and surface treatment. Surface treatment in the sense like cladding or corrosion resistance and corrosion resistance material on another base metal. So cladding, we are surface treatment also we are doing it. So in the automotive industry, for example, benefits of the laser welding for joining sheet body panels, then transmission components and chassis members that we see, that we saw in the pictures. No, so joints between the dissimilar metals are particularly common in components in power generation. So applications are vast. Applications are vast. If we are capable of doing an highly economical and efficient product by using the dissimilar joint, means that is the wonderful product. So the application is vast, even in the leading industry, rocketry or aircraft, and nuclear power plant, heat exchangers. So there is enormous applications are there. Actually, they are facing real challenges now. So laser welding is getting better advantage over conventional methods. So beam energy is deposited on the material surface, transferred into the material by conduction. So it's a hemispherical shaped weld bead is formed that decides the strength. So it's a small comparison of heat affected zone with the old methods and the new method. So the dotted line is electron beam welding. So the second one is laser welding. Electron beam welding depth of penetration is quite difficult. So laser beam welding is giving a very narrow and thin heat affected zone with high penetration without changing the base metal. So it's a big advantage. This is why we shifted ourselves. So the contrast and minimum power input is sufficient to initiate a local vaporization. So heating, then melting, these are all the things to join the materials. So this we need only a narrow gap, 1 mm or less than that, uh, for CO2 laser. So it won't affect much. It won't affect much in the base metal. So it's just a keyhole welding. So that keyhole is surrounded by a thin layer of molten metal. The keyhole is a joint, then a very thin layer of heat affected zone is there. Uh, so that is maintained by the equilibrium between the vapor pressure, surface tension, and hydrostatic pressure. That control, that thin layer is formed by the vapor pressure, the surface tension, and the hydrostatic pressure. So we are getting very thin heat affected zone because of the speed and high power. So when the workpiece is moved relative to the beam, material at the leading edge is melted and flows around the keyhole, solidifying to form a deep, narrow weld bead geometry with a characteristic of chevron pattern on the surface. That is the hemispherical. Then heat affected zone into the surrounding material produces narrow heat affected zone further. So the resulting low energy input produces a small heat affected zone with the limited residual stresses. The rapid cooling rate results in the formation not only in the beneficial fine solidification microstructure and limited heat affected zone grain growth. Then capital cost, as I told earlier, no, capital cost are considerably higher than the conventional arc process, but can be managed by increasing quality and the flexibility. So, achievability, easily. And the careful selection of controlled process parameter is necessary. As we discussed earlier, the initial setting will take some time. So after setting that, then we'll go for better productivity. Dissimilar metal joints are characterized by compositional gradients and microstructural changes. So the strength of the dissimilar joint we decide by using the mechanical and microstructural changes. So how the physical and chemical properties have changed, or how it is giving a better results. So that is the success of the dissimilar joint. That build quality is dependent on the process variable. A lot of process variables are there. A lot of nearly can do more and more. And so normally in research, we can't able to do take all the process inputs. So as per the priority level, we take the most impact process input process parameters. If it is necessary of filler material, we will introduce the fillers also. Even we will thought that it's possible, not possible to achieve these two materials. In the sense, we go for making of specialized filler materials, and we use that too. In somewhere, people are using metal foils also, metal foils, then metal powders, composite metal powders, then special metal layers, then fillers. So, anything anything we can do. Somewhere they are preheating in the everything in CO2 laser also. In laser itself, preheating. So we can achieve it. We can achieve it. So as I told, we can, if you are capable of the resource, then we'll do anything. We can do much on dissimilar joints by using especially lasers, CO2 or NDRs. So principal physical property, conductivity, absorbability, density, specific heat capacity, thermal expansion coefficient, and melting temperature. Uh, so, so these are all the basic material properties. So if you are if we are going for dissimilar joints, we should consider the physical properties of these base metals. So what is the thermal conductivity of the two materials? Then absorbability, density, specific heat capacity, thermal expansion, and the melting temperature. So these are all the major things we should consider before going for the dissimilar joint. So if it is any deviation much than 10 or 15 percentage, so we should face the problem in that area. So problem will be generated in that scope. So after a trial, so we should look for a better option. Even we can use for filler materials, preheating, or change of input process parameters. So anything we can do. So we should note all those physical properties of base metals before into the procedures. No, this. So what can we do to compensate the melting temperature? Then specific heat capacity, then thermal conductivity, how to manage the thermal conductivity. So these are all the things we should note it before, and after a trial, if it is a failure in the joint, then we do the necessary things. Then metals of high thermal conductivity such as aluminum and copper dissipate heat rapidly, making it difficult to maintain a molten weld bead. So uneven heat dissipation in a joint then comprising two metals with a widely different thermal conductivity may lead the formation of asymmetric weld bead. That is, one side will be a molten pool, another one is so solid. No, so that will break in the welded joints. So, so we should analyze the thing after trial. So we should take remedial actions to get the better joints. Long difference expansion between joint components to lead the formation of large residual stresses. So with implications for the joint strength, then fatigue properties. So the low energy heat input of laser welding reduces the size of heat affected zone in comparison with conventional, so which will lead to less residual stresses. So that will help. The melting point, then heat conductivity. These are all the major things. So first CO2 laser or laser will support the major backbone of the strength of the heat affected zone, strength of the material by supporting with the heat affected zone. First thing, it won't disturb the base metal unnecessarily. So that is the thing. So laser supports us in that manner. So we move on chemical properties. Then a chemical mismatches. That is the percentage of components. Percentage of components also an important part. So before selecting the base metal or before going for the CO2 dissimilar joint or laser dissimilar joint, we should consider the physical properties as well as the chemical properties. So chemical, but how the compositions should be the nearer one, no? Magnesium some 2 percentage or 4 percentage. No, the another base metal at least should have magnesium. In other case, that chemical component should mix up with the other base metal chemical combination. So that should happen. So that components, that will disturb the strength. So that should mix up well to form a better microstructure. So that is why we are considering the mechanical property. So that is depend on the relative atomic size and crystal size, relative valency. So that should we should consider. Not only the physical and the chemical percentage, percentage of the components also should be considered. If it is nearly close or can able to mix up well to form a better strength, means we can choose two different materials. Normally, electrics are normally harder and more brittle than primary phases. So the material phases we should consider. So the solidification, cracking, and microstructure cracks, it won't happen. No, so the malt, even though in lesser heat affected zone, the molten material should mix up properly to form a better structure. So that is the thing. Then here we are going to see about some of the dissimilar joint composition, stainless steel and low alloy steels. Joints between austenitic stainless steel and carbon or low alloy ferritic steels are required in many sectors of the industry. Stainless steel with low alloy steels to satisfy performance and economic in the area of performance and the economical criteria. There are two major concerns in these types of joints. So martensite formation in the weld bead or low alloy heat affected zone, which may promote cold cracking, cold cracking and hard cracking in fully austenitic weld metal. In the former case, normal precautions such as composition control and preheating can be employed. So, in order to avoid this, preheating before execution of the joints we can do. So, in the later, the aim is to produce an austenitic weld with a small amount of ferrite, uh, which hinders crack formation through weld metal composition. The controlled by careful regulation of the base metal dilution. So this is what our requirement to get the better strength while we joining stainless steel with the normal low alloy steels. So steel with the copper. So, what are the things we should consider to uh, join steel and copper? The joints between the steel and copper alloys are often required in marine environments, applications there, and are also required in the metal extraction industry. So, difference in the melting temperature, uh, you know, uh, nearly 400, 450 degrees Celsius temperature difference is there. Difference in the melting temperature and the thermal conductivities, as well as the compositional effects, are the main sources of difficulties in joining. So weld cracking is a particular problem resulting from the combined effects of migration of copper to grain boundaries in the steel and the presence of tensile. So these are all the challenges to join steel and copper and steel and aluminum. The joints between aluminum and various types of steels are particularly important in cryogenic applications. Then storage tanks are made from aluminum alloys. But the transfer lines from the storage tank to the medium transfer pipelines, we made up of stainless steel or nano alloy steels. So for the reason of higher strength, so we can't able to do all those things, all the complete structure with the aluminum, either steel. So there is a challenge of joining steel with aluminum. So reason of strength, control of heat flow, and to enable the attachment of valves and blows. So that can be that other parts of the valves and the valves and joints can be do only with SS, no, can't able to do with aluminum. So there is a necessity of steel and aluminum joints. So the proximity of the vaporization temperature of aluminum and the melting temperature of steel, the formation of brittle intermetallic components. So that will lead the failure of the joint. So the large difference in the thermal conductivity create problems when attempting to produce such a joints by fusion welding. So solid state process are normally used in such an applications. So steel and nickel. So joints between the steel and nickel alloys are required in power plant and electrical applications. The heat resistance of the nickel component is often the determining factor its selection. Then conductivity, majorly the conductivity. The welds between say 403 martensitic steel and Inconel 600 have been made successfully by using EN82 nickel based filler wire. So in this case, normally before this filler material. So the potential problems when welding these materials include cold cracking and reduced toughness in the martensitic heat affected zone, and partially melted or unmixed stainless steel zones, and hard cracking of the austenitic or semi-austenitic weld metal, and partially melted or unmixed nickel based zones. So these are all the existing problems. Then aluminum with the copper. Joints between aluminum and copper are often required in electrical components and radiators. Joining difficulties originate from the large difference in melting temperature and the possibility of formation of brittle intermetallic phases. The use of tin as a potential filler material. So the filler material is tin. In the solder for joints involving copper and its ability to form a electric system with aluminum. The satisfactory joints between 316 stainless steel and monel have been produced by using Inconel 82 fillers. It tolerates dilution from both both materials. So the use of high silicon 4043 aluminum filler material for laser welding of aluminum and copper and Berlin copper in an electrical component prevent solidification cracking often found in 6000 series wells. So these are all the problems and how they overcome by using conventional methods is explained here. So this is the total um, here before. So many researchers have done by joining the two different base metals and how that results came. So the total tabular column is here. So you can use it for a comparison. So there are some excellent joints, good joints, fair and poor, and then no data also that is available. So the no data available means that maybe the application may be not available, and the more vast research may be needed. So these are all the small combinations of different materials. So another material selection. So the previous slide we just saw, is it possible or not, how fair the joint is. So here then what is the problem will occur while we join for different materials. If we go for no, aluminum and silver, then the complex structures may exist. So um, these are already research done by using the conventional method. So we are take it as a challenge and the necessity to achieve with our latest lasers. In the sense, we should consider the results. So after the trial, um, we should consider these results and do the necessary things to achieve the better joints. So there is some the combination is a very useful one. So complex structure may exist. Then there is some intermetallic components formed. So they may need of preheats. So precautions we should take. No, so as we go for trial, then if it is not okay, then we should do for then we do preheat. So like that we should do some actions before execution. There's some examples: aluminum, copper, iron, and titanium. Coefficient of thermal expansion of aluminum then 23.5, then copper 17.0, no 17, and iron 12.1, then 8.9. So that value should be nearer. Actually, this is for the research purpose, but the necessity is there means we should do, or we should go for an R&D means then we just consider this. Then okay, these are all the weaker points for the joints. So we should consider. So all those physical properties we should take it, and if it is failure occurs, then we go for it and do the remedy. So another, as we discussed earlier, the input and output parameters of the welding also playing a very big role. Even after considering all those, even after considering all those all those physical and chemical properties, then input parameters, no, the major input parameters: laser power, welding speed, focal position. It's all about the CO2 laser. The focal position, beam offset, beam angle, shielding gas, flow rate. These are all the input parameters. So then we have some output parameters to measure the strength of the steel, tensile strength, depth of penetration, weld bead area, then bead width, micro hardness, erosion, then welding operation cost. So these are all the output parameters which are against the input parameters. So we should get satisfied with the with those output parameters based on the requirement. So if it is more, if we are in need to consider that welding operation cost with more priority in the sense, we will take it. So then depth of penetration, then more hardness, erosion. If it is a need of erosion, then we do joints and go for erosion and all. So the laser nozzle, then weld feeder. Weld feeder angle is there. If it is weld feeder, then weld feeder angle will be there. Then weld feed speed is there. Input, as we can take that to the as a input parameters. Then laser beam focal position. Then the position angle, power. So lot of input parameters there. Then I just to give the some for the example. So it's a weld bead geometry. So weld width, then heat affected zone, depth of penetration. Uh, so these are all the measures, output measures to uh, finalize the also to judge the strength of the joint. We should measure it the microstructure, no? So macro by using the microstructure, we used to measure all those things and to do calculations with better strength and to measure the weld bead geometry. We are going for it. So, it's the major application. No? Normally before, it's a heat exchanger. It's a pure nickel is widely used in evaporator of soda production. The pure nickel is using necessary now. Nickel is used for the whole heat exchangers. So there is there is no need to make the high cost material to produce the full heat exchanger as a single material. So if it is possible to do the better joint with pure nickel with stainless steel. We go for stainless. Stainless steel means that's highly economic. No, stainless steel is a better having better price when comparing with nickel. No, so the main thing we are using this for the thermal conductivity, heat conductivity. So the main core is that tubes. You can see now that tubes. So that tubes we can make with the nickels. So if we are capable of achieving a better joint with nickel and stainless steel means, so we can do a joint of that nickel tube with that tube sheets. So by the way, we can do better cost cutting and good efficiency of that heat exchanger. So that is the major application for pure nickel with 316. So I am willing to discuss some of my research work on that, similar with the CO2 laser. So it's a very only the 2 or 3% of work with the materials which is required to join, as well as the process parameters. Then now, as we discussed earlier, we have more number of input and output parameters. So we considered few. So I used a nickel 201 stainless steel 316, the 4 kilowatt laser. I used to plate thickness 5 mm. So it's a chemical composition. So chemical composition is there. So by considering that application, just I wanted to achieve it. So that is the most wanted joint. So nickel alloys with stainless steel. So the better joint of that dissimilar joints is the recent trend. So we can't able to make the nickel alloys as per the I do that is available in openly. So and application is there, so we go with it. If you are going for compositions of nickel alloys, no problems may arise unexpectedly. So go with the available one. Then physical properties, density, melting point range, specific heat, then coefficient of expansion, then thermal conductivity, then electrical resistivity. The major challenge I No, I faced with SS is the reflectivity. I didn't consider while I go for the experiment with the dissimilar joint. The major problem is the reflectivity. Why? Because we have the reflecting mirror and focus on the top of the machine. So when we go for 90-degree, the problem arises. So we managed it. Then mechanical properties. So stainless steel 616, nickel 403. So how we are? So the two different materials having the two two ends of different properties of chemical composition, mechanical characteristics, and physical properties. Then how we are going to judge the strength? Judge the strength of the joint in the sense, at least any the no where we are going for tensile strength, mm, the broken edge neck should be formed at least any one of the base metal. If it is 316 is much better. It's much better, but at least we should have base. First, so it's only a trump of machine, a trump of laser cell, TLC 1005, 4 kilowatt CO2 laser. So it's no work. It's a trial runs. So I told before going for new things, then we do trials to set the input parameters. So it's a new one for the machine side also. It's a new one, so we should finalize the upper and lower limit. Then number of trials done and not able to get the proper joint. So by the way, after getting some references, I got the point of the third one, position of laser beam. Position of laser beam, it's 0.15. The position of laser beam is not in the gap between the two materials. Just I concentrated on nickel side. First, nickel will just 0.15 mm towards nickel. First, nickel starts melting. 1 minute. Why? Because the melting point of nickel is quite high. Nearly 1400 plus. Then melting point and conductivity, then thermal conductivity is much high in nickel when comparing with 316. So for that thermal conductivity reason, they used nickel as a tube, and so there is no way. Then the whole heat exchange is made of nickel. So it's for that reason, 70. It's a major difference. Thermal conductivity, 16 is there and 70. So for that reason, after after more trials, then we try to move the laser concentration on nickel side first. Then it's okay. Then laser beam angle, we set not able to get at 80, 90. We just reflectivity, so not able to transfer the energy properly on it. Then again the focal position. So focal position, normally in lasers they do on the 0 to 0 on the surface simply, but here in focal position, after more trial runs, it's we done into it minus 0.75 from the surface. So by the way, get equal penetration. So one side getting more molten pool, another side solid is totally not helpful. So these are all the things for the initial stage. It's a struggle for similar time. So type of variables for better strength. So for optimization and the process trials, 5 level process optimization. Then we done tensile, impact testing, bending testing. These are all the mechanical properties to judge the strength. So we done as per the standards. So for tensile, um, then comparison of tensile, we just compared the tensile strength of the dissimilar joints with the base metal. So we received the failure. We got the failure at the nickel joint. So definitely options are there. So definitely we may conduct preheating or we use better fillers. If it is possible to do with the same process means achievable. So it's highly achievable uh, to get the highly achievable for a better strength. We may get a failure at the SS side. So we got a failure in the nickel side. Actually, before that, we do more combinations with the more materials: nickel with aluminum, MS with copper, copper with nickel, uh, then MS with nickel. So we do things, but it take more economically, but it's much cost. So finally, we decided with this. And the micro uncertainties in the microstructures we found a lot in the indoors materials, no aluminum with nickel, nickel with the copper, and we can't able to find the proper application for the place in that area. So it's a strong application of nickel alloys and normal steels. We have better applications there. So it's a sample the weld. There's a failure in the weld, then closer to nickel and the parent material nickel. So 412. It's good one. So it's not necessary to no. It's really quite complicated to get the achievement in the similar joint. But normally, experts are saying that you can't expect the failure in the similar joint in the base metals. If you are receiving the same means, it's much better. But at least your weld strength should be the 74 percentage, no, 75, more than 75 percentage of the any one of the base metal. So that is much okay. If you are getting the tensile value of the joint as 75 percentage and more of the any one of the base metal, then joint will be good. So that is the thing. Then impact toughness. It's a measurement. So, macro structure, we measured it and calculated the weld area. Then measurement of microstructure. Micro harness, same. In weld area, quite high. This um, formation of graph should be expected. So it depends on the left side and right side of. If it is left side, the left side I measured the stainless steel on this side. Then it's a weld area. So graph comes like this. While in the heat affected zone, it's quite high. Then in the center of the base metal, I started from here. Then closer to at the center of the weld bead, then it's gone down to the base metal hardness. microstructure, macrostructure. So in macrostructure, usually you can find the issues, how the fusion is there, then is there any weld shrinkage or cracks inside the depth, then offset, then how the weld area is. So, um, no, porosity should be there. So porosity is there. That porosity should be in a limit. So if it is more porosity, that too leads joint failure. So, so if it is more porosity, there may be the reason of no more speed. So if you are seeing more porosity in all the trials, nearly done 30, 40 plus. So now all the trial runs means no, then we should control the speed. So it's a mix up. No, it's a joint. It's a joint base metal weld and nickel side. So this picture, then is pure nickel base side. Then for the sample, another one sample, weld and nickel side. Then mix up should be there now. Mix up should be there. So if it is a proper mix up, then we good. So if it is, so there is some uh, improper mixtures there now, we'll see the failure in the weld itself. So proper, we are expecting proper mixture. So it's another one. So it's a trials. So the optimization, the model validation. So actual resist prediction. Yeah, we will predict and predicted. Then error should be there. So error should be in a limit, right? And by optimization, we can compare the uh, process input parameters, how the penetration or bead width or depth it's getting changed depends on the input parameters of power, laser speed, how it is varying. So by the way, we can adjust the things. So not able to do no more trials. No, it's a objective of optimization. So by using this, we can find the most impact process parameters, which is playing the major role. So the same, no, response plots. So this is the thing. Beam power. What is for optimization? What we need? Beam power should be minimized. Welding speed should be maximized for more production. Beam power should be minimized for economic to reduce the economic cost. And focal position should be in range. Beam angle should be in range, which we found. And beam offset also. Beam offset. And depth of penetration should be maximum. The full. Then bead width should be minimum. Then focal zone area minimum. So focal no, sorry, fusion zone area. Fusion zone area should be minimum. If it is maximum, then more affection of base metal. So it's a area measurement, fusion zone. These are the trials and then again predicted value. So in microstructure, so epiaxed grain, then annealing twins are there. So these are the and then austenitic also. Then coarse grain columns. Coarse grain columnar growth forms is like a helping hand. It's a bonding. So that creates better strength. So there is some delta for it also. So and traits are there. So both column better. So it's another one uh, advanced tech. Actually, it's a combination of most advanced, no? Aluminum with steel. So previous research only on 5 mm plate. Both plates are same size. So here we can see 2 mm of aluminum and 1 mm of steel. A nice variation. So for that, they used preheating method. Preheating method, no, by using tick torch. Uh, so tick torch they used for preheating, so with a 60-degree angle and welding direction and heat resistance. So the preheating or post heating, both we can try, which depends on the failure, the material. We try both. It's all trials now. So preheating or post heating. So it's called an arc assisted laser welding, brazing of aluminum to steel. So in addition of the assisted arc, the temperature field distribution of the base metal surface becomes larger and the single laser process. So and the maximum temperature of the molten pool reaches. So we are raising the pool temperature. Yeah. The heat input from the arc can increase the spread time of the molten metal in the welding pool. That helps us. So this is after single laser. Only the two comparison with the single laser and arc assisted laser. So there are two comparisons. Now we can visually we can see there is a problem with the seam weld seam. So here is a better mixture with the better mixture of dissimilar joints with the steels. So it's an weld pool now equal. The elliptic thermal view is equal. Then arc assisted laser is giving more strength. It gave no 1.3 times than single laser. So the small setup of preheating or post heating may give very good results. Now 1.3 times more than the base metal, which is very good. No, then here in conclusion that lasers are used different years. No, 201 and 306. No pillar rays were used in that. So we can try. We can try with filler, preheating or post heating, or foils. I tried with nickel powder, no? Nickel powder, or filler may have better alloy. So anything we can try for it to get the better results. So it's highly possible, highly possible. So it's a basic research. But for quite high, if you are doing a filler material or foils or powders or preheating, heating, so that better we can. So okay, same thing. Uh, so there is more vast research area is there in dissimilar giants. I'm not saying that only CO2 or normal lasers only can do with dissimilar giants as we discussed now, but it's supporting the main backbone of the strength of the giant. That thing is the heat effector zone. It's supporting heat effector zone. That is the first thing. So that's why I'm saying that lasers are better, not only CO2. If we're going for thick plate up to 25 thick plate is there or thick pipes are there, go for CO2. Or even lesser thickness, same here. So lasers giving the first main thing is okay, thick. Then what is next? How we are going to manage the different difference in physical and chemical properties. So what can we do for the different metal compositions? So how can we manage it? So what type of filler can we use to compensate the material differences? So these are the things we should consider and do for the research. It's only now this session only 1% of the information There are a lot of opportunities are there. You are capable of no, give a better product to the nation, ISRO or aircraft parts and nuclear power stations. And if you are no, if we are capable of um, no, doing a better heat exchanger with the dissimilar joints, that's the basic. So we are normally doing more application. We are using more heat exchangers in the common applications. Now we are using vast application in the heat exchanger. Just in change of material with a better strength, will I think I am not in the field of thermal. Uh, we can do. No, thermal people can do the thing. It's a combination of mix of disciplines in engineering fields giving better products. So by the combination of our fields, we give the better results. So with the assistance of thermal people, with the production people, can do the better and the effective heat exchanger and other products. So my main application is heat exchanger. Then there are more materials are there and alloys. We can create new alloys also. So in composite materials, then production and manufacturing, then thermal. So everywhere the scope is there. Okay, sir. So thanks for the patience. Listen. Then initially we got some disturbance in the net. Sorry for that again. Then I just skipped some of the slides also in short of time. So, sir, thank you so much for the management, sir, and the coordinator, principal, sir, Manivel, sir. Thank you for giving the opportunity, sir. Thank you so much. Any queries, sir?
Sir, thank you for your valuable input for how mastering the art of joining dissimilar material using CO2 laser system. Sir, share here we are clearly taken away the points about material properties, laser processing system, joint characteristics techniques, process optimizations, many applications of laser system, and failure mode analysis. Through your presentations, how to select the materials combinations to make a better weld or joints, and it's through the microstructural analysis. Thank you for your presentation, sir. Valuable presentation, sir. This is questionnaire session. Dear participants, if you have any queries, you can ask with our resource persons, or you can put your queries in the chat box. He will be ready to answer your queries.
Sir, good evening.
Good evening, sir.
I'm Srinivasan from RES College of Engineering. So mostly metals are reflective in nature, but we are using actually laser, but laser has a problem with reflectivity. How we can manage this thing with materials, particularly metals?
Sorry, sir. Actually, materials.
So
Sir, come again,
actually,
sir.
mostly metals are lustrous and reflective in nature.
Rust, no, sir. Corrosive.
No, sir. They are reflective in nature. Metals are reflective in nature.
Reflective. Yeah, yes, yes.
Ye- Yes, sir. But laser has a problem with reflectivity. How we can
Hmm.
manage this?
Sir, yes, sir. So, as we saw in the slides, no, 90 degree, definitely, sir. I didn't expect that reflectivity issue in my research, sir. But the major problem no, I face with no, nickel is not a problem. Nickel is not a problem at all. But in
This is
SS316, SS I faced the problem. So even we stopped the mission. So now just we changed the angle. No, only 3 degree we reduced. You may see the process variable instead of 90 degree. I didn't take that 90 degree as a laser beam angle. You can just
okay.
incline the angle, sir. Then by the way, reflection will go that side.
So will it affect the penetration depth, sir, by changing the angle?
No, no, sir. No, we achieved, no, sir. We made better giant, no, sir. In the yeah, so otherwise, no, roughing of the material we may try. Well, initially, they told, sir, there is no more. We used to rough the surface of the material like that. They told, but we didn't do that. We just changed the angle of laser. We achieved, sir. Okay. We can play with the angles, sir. We get it. We'll get it.
Okay, sir. Thank you.
Yes, yes, sir. Thank you.
JK sir, another question from Nilesh Rane. Which optimization techniques and DOE method have you used in your research?
RSM, sir, response surface methodology, sir. Even though artificial neural networks or fuzzy logics, more methods are there. But response surface methodology is better, sir. RSM work. RSM is very helpful to find the better process parameters, sir. I used the RSM, sir. Nilesh Sani, sir. RSM, no, DOE 11 software.
Thank you, sir.
Thank you, sir.
Any other questions from participant sides?
Sir, in this area, one more thing, sir. So in this area, I find problem of finding a machine. There are no machines. No, only one machine in the South India. There are Magar lasers in Bangalore, sir. In South India, all South India, that machine available in Magar laser Bangalore. They are available. So we just gave a proposal that it's a conjoint research that they asked only for combined publications and the acknowledgements. So they supported that. So if you are really interested on that, sir, please refer Magar Lasers, Bangalore, sir. On this research area, if any doubt or any discussion or any suggestions, please get my number from Dr. Singh Manival, sir, the coordinator, and mail ID also you can get it. So then I will give, sir. Oh, no problem, sir. Can I give, sir?
Yes, sir. Thank you. Thank you for your valuable input, sir.
Yes. Okay. Number, sir, please. Thank you, sir.
Prakash, sir.
Sir, maybe, sir.
Can we continue the next session?